Hello everyone and most welcome to the Heidegger series. Today we will make an interview with Professor Petter Mostad at Chalmers University, and we are going to take up some questions from your viewers and some questions I came up with, and also Petter himself, about Bayesian statistics and mathematics, I think you could say. Petter, could you welcome to the interview?
Thank you.
Thank you very much for coming. Very appreciated by you. This lazy summer's day here out in the woods. We are very interested since the first interview, maybe half a year ago, where you for the first time let us into Bayesian statistics. You had one thing here about the, as you said, perpetual fight between the Bayesian and the Frequentist. Could you that lengthy explaining of that, please?
Yes. So I was actually going to start with, take this way back and start with a different question.
Oh.
So I will pose my own questions here.
Please do.
Yes. So a very basic question is, what is statistics? And I think there are at least two common interpretations of this. One is, putting together data, listing. If you collect some data, you want to summarize it into lists or graphs or numbers. However, and that's very useful, and that's what most people think about when they say statistics, but it's not really directly useful if you think about it, because what you want to use statistics for is to predict things. You want to learn something that you can say something about. You want to use it, and then to use it you want to be able to predict something, or what might happen in the future. Or if I ask this question, if I know that if I have a statistics that 90% of some people will vote for a certain party, then that's what I really want to know, is what is going to happen in the election. Or if I ask a random person, what is that person going to say that he or she is going to vote for? So in some sense, what you want to know, if you want to have something useful, is to make predictions. And what kind of predictions can you make? Well, these are probabilistic questions. So then you want to say, what is the probability that something will happen? This is a very basic thing, and that is the goal of what we call mathematical statistics. So that is that when you use summarization of data together with probability theory in order to make predictions. And that is the kind of statistics that I'm focused on. So then we get to the second question, which is more basic, and that is, what is probability? Because now we want to use probability as a kind of, we want to say the probability of this and this happening is 50% or 87.3% or something like that, as something that concerns the real world. And what do we mean by such a statement?
Yes.
Now we get to your question.
Yeah.
Because now we get to the fight between the frequentist interpretation of such a question and the Bayesian interpretation of such a question.
So if I get it right, the frequentialists are the ones who do, so to speak, classical statistics, or gathering data and frequencies.
Yes. So the history of these two schools of thought is that we had early on in the history of mathematics, people thought in a kind of Bayesian way, and then there was a Fisher, who started about 100 years ago with the P theory, P values and such things, and that started a kind of frequentist school, which was dominating up until a couple of decades ago, and now it's more, I would say, maybe more Bayesian, but there's still a big conflict between those two schools. And the contents of these schools is that the frequentist answer to the question what is probability is that it is the frequency of something.
Okay.
Yes. So if you want to assign the probability to, say, getting a 6 on when you throw a dice,
yes, the throw of the dice,
then you say that it is 1/6, because if you throw it 1,000,000 times, or at least 1,000 times, then the frequency with which you get the 6 will approach 1/6.
So it equals out in the long run.
Yes, yes. So then
you need to do it maybe for an extensive time, and then it equals out.
And importantly, it has to be a repeatable event.
Yes.
Right? So in the frequentist universe, you can really only assign probabilities to something that can be repeated many times in very similar ways. And of course, that's when you throw dice or play cards or do a number of experiments, you can either repeat them or you can at least imagine that you repeat them. But this idea gets into trouble when you want to assign probabilities to things that are not really repeatable.
No.
Right? For example, you can say, what is the weather tomorrow? We can say it's a 20% chance of rain. People say that all the time.
Yes.
But what does it actually mean? Because there's only one tomorrow, right?
Yes.
Either it's raining or it's not.
No.
So you cannot really...
You cannot repeat tomorrow.
Yes. So that kind of interpretation of what you actually mean is difficult in a frequentist setting. And it's also, I mean, I've been working with geology, for example, and you can say, what is the probability of saying a fault line in this place? Well, we can have models where we say that the probability is like 10% or something. But of course, the fault line is either there or it's not. We just don't know.
Indeed.
So then we come to the Bayesian interpretation of that, and this is focusing now on knowledge. So what we say in the Bayesian interpretation of probability is that it is a feature of somebody's knowledge about the real world, not the real world itself. So we say that when I say that the fault line has 10% probability of being there, it reflects something about my knowledge about that fault line or the geology of the area. Or when the meteorologist says that it's 20% chance of rain, it is a reflection of that knowledge of that person. So importantly, the Bayesian interpretation of the concept of probability is individual, because it's necessarily connected to knowledge, so an individual's knowledge. And already we can see that there is a conflict here, because the frequentists will say that, well, we are scientists, we are objective, and we only think about things that can be objective in the real world.
Yes.
Which assumes that there is a real world and all of these philosophical things.
And that real world is also repetitive.
Yes, and you can repeat things, right? And then Bayesians say that, well, we say that probability is connected to people's knowledge about the world, which is separate from, the people's knowledge about the world is separate from the real world, right? So it is a huge conceptual difference between those two.
It's a chiasm.
Yes. And so historically there's been lots of discussions back and forth. But and we can come back to that. But really, the important thing is, maybe I should say something about what Bayesian statistics is and how it works.
Definitely. I was actually waiting for that thing there. Thank you, Petter.
So, because you want to compute with it, right?
Yes.
And what you can say is that it has to, first you have to assign some kind of subjective probability to things. And for example, if you talk about throwing dice,
yes,
you can, of course, you can compute the probability of getting Yahtzee in the first throw, and that would be computed based on an assumption that every dice has a probability 1/6 of having each of the different numbers. So what you do then is that you make an assumption of some kind of what we call a prior in the Bayesian
a prior,
a prior probability assignment to what you believe, and then from that you can make computations. And the key thing in Bayesian statistics is conditioning on data, so that if you have a well, I forgot to get good examples here, but if we continue with let's take a card game, for example. You can say that, well, any ordering of a card deck is any ordering is the same probability. That would then be your prior in this case.
Okay.
And then you can compute what kind of hand you have. But let's say that I know that you then play, if you have five cards and you play like Queen of Spades, then I can well, no, maybe that's not a good example. The thing is that sometimes you can have you get information about the possibilities. You have a sort of a set of all the possible states of the world, which have assigned probabilities from the prior, and then you get some data, and that data will tell you that not all of these possibilities are possible.
Ah, yes.
Only a subset of them. What you do then in Bayesian statistics is that you update your knowledge about the world
yes.
by discarding all of those that are impossible and saying that the remaining ones are possible, but you scale them in such a way that the relative probabilities of each of those that are still possible are the same as before. So this is a small bit of mathematics that is here. You take the the subset of those that are possible, and then you rescale the probability so that they sum to 1, but they have the same relative probabilities within the set that is possible. This single computation is the only one you do in Bayesian statistics. This is it. You don't do anything else in order to take into account data and learn. So the learning process is simply to discard things that are no longer considered possible based on your data.
Yes.
And rescaling the probabilities that are possible.
That's the only feedback.
That's the only way you learn. This is called Bayesian learning. And so this
it's even a special expression, Bayesian learning. Then.
Yes. Yes. And this is the thing that is sort of considered a natural way of learning. Now, in frequentist statistics, you don't have this idea at all. You want to have you want to make estimates of things, and you want to know how reliable those estimates are, and then you have to make some assumptions about that and so on. Maybe I won't come too much into that. But,
no.
But
I say okay.
The thing is that many of the computations that you do are actually the same, so that in terms of numerical conclusions, you will often get sort of the same or at least superficially, you will get the same conclusion. As we discussed, the idea of probability will be fundamentally different.
Yes.
So in that sense, the conclusions will be fundamentally different. But in terms of interval of confidence or credibility or something, numerically, when you compute it, it's the same interval.
Ah, yes.
So it seems like it's very close, but fundamentally, philosophically, it's different.
Ah.
Now I've been talking a lot, and
Yes, yes.
you can rein this into more.
Oh, yes, it's getting even more interesting now. Thank you for that introduction. There is a resemblance here, the paradigm shift that was in physics, because classical physics absolutely depends on repeatability, all of it. Every single thing is assumed to be of two aspects, linear and repeatable. And then came quantum physics, and it showed that nothing is linear and nothing is repeatable. Not a single experiment is repeatable. So it's a nice parallel here, which makes it even more, how do you say, broad in its take, so to speak. And it's a bit like, as you say, philosophical questions.
Yeah.
Is there, in the classical model, there is a world that is strictly out there. Our knowledge of the world is not interesting.
Yeah.
It is out there still.
Yeah.
It has been there out there since the dawn of humanity, even before, and it will remain the same after humanity's gone.
Yeah.
Whereas, if I understood it correctly, more or less, in the Bayesian approach, your knowledge is taken into consideration.
Yes, and I would like to add in this context that the Bayesian paradigm does not say that the real world does not exist.
No,
It does not say that. I mean, you can keep that philosophical attitude. It's just saying that when you make predictions and when you compute with this, it's not really that thing that is the focus. You need to focus on the knowledge.
Oh,
of the
yes.
world. And I think that is a connection with quantum physics.
Oh, yeah.
So you really focus on the knowledge, and that means that you don't really need to. I mean, you avoid a lot of philosophical paradoxes about defining this real world that we can never reach or never completely observe.
No.
Because it doesn't matter. We are focusing on our knowledge about it.
Yes. It's absolutely brilliant, and as you say, it doesn't say that the real world do not exist. And we had that quite recently when it came to the Nobel Prize Committee, when they were supposed to write something understandable for the press and media. Why these three people got the Nobel Prize. And they actually wrote, they prove that there is no reality, which is wrong. And everybody was rather upset and everything. But it's a different kind of reality, but even more real, or however you want to express it. But there's still a reality. So it's another parallel. Very interesting. And how do you work with this since how long time, and how did it begin with you? How was your first experience? Didn't you like it in the beginning?
This is also an interesting story maybe for some, because my background is in mathematics, and I actually did not know any type of statistics, before after I completed my PhD in mathematics.
Where was that?
I completed my PhD at Princeton in the US. In a completely different field, in mathematics, in pure mathematics. And then, for various reasons, I started to do statistics. And as many people who has a background in pure mathematics, I preferred Bayesian statistics, the Bayesian paradigm to the frequentist paradigm.
Wow!
Because for me it was more. I mean, to me, the classical statistics is a little bit undecided, because you make a lot of choices when you set up the theory for estimators and for choosing what is good statistics and what is not good statistics or mathematical statistics, in a rather ad hoc sense. Whereas in Bayesian statistics you only make one assumption, and this is the one that I told you about, that you have this sort of individual knowledge connected view of probability, and then you do the conditioning on data. This is the only, this is the connection between the mathematical theory and the real world. And after that, it's all mathematics.
Yeah.
And this is what attracts me as a mathematician to Bayesian theory, because you separate out the sort of the messy applied stuff.
Yes.
From the mathematics, which is, once you have made your model of the world as a probabilistic model, then everything else is mathematics when you condition on data and make computations. So I think that this is not referenced anywhere, but my impression is that people who have a background in mathematics are more into Bayesian statistics than people who do not, because if you have this sort of mathematical background for a long time, then this separation is valuable. So this is my background. I started with statistics after my PhD, and now I'm a professor in statistics.
Well, I can understand that, because you have to do these ad hoc things, and they're sort of ugly corrections from.
Yes.
And
and different people have different opinions about what is good, and then you have to sort of, well, this professor says this and that professor says that, and
it never ends.
And this is not attractive to a mathematician.
Yeah. I think that's very helpful to tell about your personal experience of this, because sometimes when something gets very abstract, it helps to have a personal experience, so you can get into the feel of it. So there's a different feel to the Bayesian, to the frequentialist approach. Very good. I really like that.
Good.
Now we're going on a limb here. I got a question here from Henrik Gustafsson. It's rather complex, and it's a very specific question. What about the fact that Bayesianism rests on the rules of probability, and we have to use induction to show that they will continue to hold? Hence, it presupposes uniformity principle and is circular. I'll give it to you here. It's rather cumbersome.
Yeah.
I think he put away a lot of thinking on that question.
To show I'm not actually quite sure if I understand the question. But I mean the circular part, I mean, I'm not sure. Let me say something that might be connected.
Oh yeah, please do.
Person. Very good. Because this is the only thing I do. I mean, he could reformulate this question, and then we can because I mean, a circular argument in this case would be that you assume that you have proven, say, that the world is Bayesian, or that Bayesian thinking is right. You don't.
Very good. I think that answers the question. Yes.
At least in my view, because from my point of view, Bayesian statistics is simply an applied science. So it's simply a way to use mathematics in such a way that it seems to be useful in practice. And so there's no argument anywhere that it's true in any sense.
No.
It's not. It's just simply useful. It's an applied science that is useful, has proven itself to be useful in a number of cases. And then of course you can go back to the previous discussion that we had. Has frequentist theory proven itself to be more useful than Bayesian, or the other way around? And that is actually a very good question, because if you use this in practice, it's not necessarily true. I mean, what I said about the prior is very it is a very difficult question, because it involves a lot of stuff. So it's not an obvious answer to that one, because then it's really a practical question, right? What is most useful in practice?
Yeah.
That's another question that we could, or I and he could discuss more clearly. But I mean, the philosophical, if we try to separate out the philosophical part, it's that this is not something that is pretending to prove that it is true.
Okay.
It's simply an applied science. So I cannot imagine that there should be some kind of circularity here. But really, if he could come back with a more clear, a differently formulated question, or with more parts, then I could.
Fair enough. Thank you. And then it's a sort of indirect, not really question, more like a speaking subject.
Okay.
A sort of synchronicity. I got an email from my friend Jan Eiskens in Antwerp, Ghent, and it's from a new trend within a completely different area.
Yeah.
So that's why I said it's more of a discussion subject, and it's from science of cognition and neurology and brain research. And to oversimplify things ridiculously, it was, when I studied science of cognition, it was almost like it was more in the classical model. It was assumed that the human being was a sort of camera that depicted things from the so-called isolated outside, that our knowledge of it, our skill of understanding it, how our brain structure were not of importance. It's just sort of simply reflected the outside.
Okay. Yeah.
This is a bit like the frequentialists, and that has changed very recently. And people start questioning, what would that outside be that has no connection with our cognition?
Yeah.
And one who went in that direction is the Hungarian-American scientist György Buzsaki. And in this mail, it was hinted that he implied that the brain actually worked in a Bayesian way, and try to get away from the idea that it's representation. It makes frequentialist calculations of the reality. For instance, if I see a cup, is that a cup based on the grayness, the roundness, and I got a million factors? My brain is like a immense IBM computer, like the deep blue, and calculate, it's a cup. And instead, it's Bayesian, and our knowledge come into the whole thing. And it's been a tremendous change within the science of cognition. What would you think about that spontaneous? Sorry to put you on the spot.
No. I think it's a very interesting topic, and I actually think that it illustrates my sort of Bayesian worldview. That I mean, you cannot really construct. I mean, the structure of the brain, how it is wired when we are created, when it grows, is fundamental. That's a fundamental ingredient in what kind of output. Because, and this is parallel to the prior in Bayesian statistics, that you cannot really get anything from nothing.
No.
Right? You cannot have a brain that works as some kind of universal blank slate,
No,
and then
no.
sort of just loads and then magically creates structure.
No.
So the structure is already there in the wiring of the brain,
Yes.
or in our what evolution has brought forward in how our brain, our what's it called,
Our makeup.
Yes, and our how we act spontaneously,
Yes,
right,
yes,
without
yes.
learning it.
Definitely.
These things are hardwired into our brain, and we couldn't actually have any kind of learning without
Those things being
those
present.
things. Yes, and then on top of that comes the learning ability. And I agree with those that believe that this learning process of the brain is best modeled as a Bayesian learning,
Okay.
because then you have all of these you narrow the ways that things could. I mean, first of all, our brain is kind of probabilistic. We believe that something might happen, so we're afraid of it, but we're not sure. It's a very natural thing to think probabilistically, I think, even though we don't necessarily put numbers on it.
No.
But we think that things might happen or they might not, and we act on this uncertain information. So handling of uncertainty is something that is, I think, inherent to the way
the system, yeah.
The brain is constructed.
Really. Yeah.
And then, given that, then you can say that, well, if we see something more times, then our belief in that is strengthened, and other beliefs are weakened. And I think I'm not an expert on that, but I think that there has been some research, comparing, explicitly the learning process of, natural learning process of people with a formalized Bayesian version. And it's not true that we are always perfectly mathematically Bayesian in our thinking.
No.
But still, what you can see is that the more rational you want to be, the more sort of mathematical you want to be in your thinking, the more you are forced into a Bayesian way of thinking. Because there's no, I mean, the only logical principle you can apply in this kind of learning process is this Bayesian conditioning on data that we mentioned before. And so I think that some people have argued that, again, I don't have the reference, but some people have argued that the brain is basically a Bayesian learning machine.
So there was two things in one go. First, we were really pointing in the direction of György Buzsaki, but it's also another assumption within the science of cognition. It's called the blank slate. And it's the idea, I would say, inherited idea, never really formalized, that all humans are born as completely blanks. We have nothing in us. But instead you seem to lean more into...
Absolutely.
You do, yeah.
I cannot imagine how one can even construct in a reasonable way a theory of learning if you start with a blank slate. This is my opinion.
Yeah, when you say it, and I've been thinking about it too, it makes more and more sense.
Okay.
But when I studied science of cognition under Peter Mostad in 1997, blank slate.
That was theory.
It wasn't even expressed. It was how do you say, självklar.
Yeah.
It was obvious that that was the thing. And we used computers which you can nullify, but you forget that there is a caretaker of the computer.
Yes.
There's somebody
and the computer is mapped to reality in a particular way. And
exactly. Yes.
Is very significant in the way that the computer works and how it learns.
Indeed. But oddly enough, we're not aware of that. And there were computer scientists on the program, and sometimes you just lose out what you're working on. And then it was rediscovered, so to speak, that they are programmed towards a certain area, as you say. And there is somebody managing the computer as well, and somebody constructed it as well. And none of these three things apply for a human being. Like Hans Johansson wasn't constructed in a certain way.
No, but you were constructed in a different way.
Yes.
And that construction is what really is important. To the way you learn.
Oh, very great. Maybe we should let people have some question and we can get back to you at some instance.
Sure.
Would that be okay?
Yeah, absolutely. It's fun.
So, well, thank you very much. And, well appreciate, Petter. Thank you very much for taking your precious vacation time here. And now the sun is out again.
So we'll go swimming now.
Yeah. Thank you. And bye-bye.